Hello, welcome back. The title here is called Slope as the Rate of Change of a Function, Part 1. Here is where we start to connect the dots. We've talked about functions, which, are just like input-output, machines that calculate things, and we can graph them and see what they look like. Here we're going to start talking about the slope as the rate of change of a function. Now, I'm being totally honest when I tell you that what we're talking about right now, even at this lower level, is absolutely the basis of what we call calculus later on. When you get through algebra, and you get through algebra 2 and geometry, you take a class called calculus. The entire basis of it is really what we're talking about here. But this is not hard. Don't get so scared about it. It's very, very simple. It's just slope, essentially slope. We've already talked about slope, but we're going to extend it to kind of like a new little area in thinking about slope in a different way than we've learned before. But trust me when I say that the very first chapter in a calculus book is all about rate of change, how fast some function is changing. We use that kind of thing to study more complex situations. So before we go any farther, let's just do our first problem. I think it'll become a little more clear. First problem, the table below represents a linear function that shows the relationship between the number of tickets to a movie, X, and the total cost of those tickets, f of x. So you see what we have here is an input-output table. I've already filled it out for you, but basically the input is how many tickets I purchased, 2, 3, 4, 5 tickets. I could continue the table if I want. And then the output, which is the f of x, the function of x, the number of dollars it costs to have those many tickets. So if I have 2 tickets, it costs $4, but notice if I double the amount of tickets, it's double the amount of dollars, so it's $8. So this is a linear function. It means that when we graph it, it's going to form a straight line. And it makes sense that it forms a straight line because every ticket costs the same amount. So if you increase the number of tickets, then the dollar should increase, in a lockstep way proportional to how many tickets I've purchased. There shouldn't be any curving going on because every ticket is another X number of dollars that we add to it. So first we want to calculate the slope. Now, we can calculate the slope using any numbers that we want here. It says here it's a linear function, so we already know that if we find the slope using these 2 points, and we find the slope using these 2 points, that we're going to get the same slope. So let's just do that and just see what we get. Let's remember what the slope formula is. The slope is y2 minus y1 divided by x2 minus x1. We've done this many times before. All this means is how fast is the output going up, meaning we subtract the output values to figure out how much the output goes up. The output in this case is dollars. And we compare that by division to how fast the input is going up. This is rise over run. How fast is the output going up compared to how fast is the input going up? And we can use whatever points we want. We're going to use, let's use these 2 points here. This is 3, 6, so I'll just put over here 3, 6, and 4, 8, like this. And it also doesn't matter which way you do the subtraction as long as you are consistent. So let's put it in there. These are the y values. So just to make it easy, we'll do 8 minus 6, 8 minus 6, and then we'll do 4 minus 3 for the x values, 4 minus 3. If you're not sure about slope of a line, go back to my lessons on calculating slope. We did lots of lessons on this. You should already know this. We've done this before. All we're doing is figuring out how fast is the function going up, the y values, the dollars, by subtraction, and compare that to how fast the x values are going up, which is basically the input, the number of the tickets that we have. So what we have is 8 minus 6 is 2, and 4 minus 3 is 1, so we get the answer of 2. So the slope is 2. But let's think about what it actually means, okay? What we have subtracted here is dollars because we were subtracting these numbers. So on the top, it was dollars. So I guess I'll put, here I'll put for the units, it was dollars subtraction per, and then what were we subtracting here? Tickets, the number of tickets. So this is tickets. So when you actually calculate the answer, you get a unit of dollars per ticket. So this is dollars per ticket. And the way we write that mathematically is we say, dollars per ticket. When you see a division bar like that, you read it as per, so $2 per ticket. So that's the point of this lesson. We're going to graph it in a second, but I want you to start thinking about the slope as the rate of change of something. How fast is something changing? You have to have units to understand rate of change. Think of kilometers per hour. That is a rate of change. How much does my distance change compared to 1 hour, or unit of time, hours? Let's talk about temperature per second. If something is cooling down in the freezer, how fast is the temperature of that item going down per second? That's a rate of change. Something per something. In order to have a rate of change, it has to be comparing two things. Miles per hour, dollars per ticket, temperature per second, feet per, I don't know, light year, something. Two things have to be compared in order to give a rate of change. In this case, it's dollars. The Y values are dollars, the X values are tickets, dollars per ticket. And this is going to represent something important when we plot this thing. So notice, first of all, that we could calculate the slope using any other two numbers. If we use these points here, we would subtract the Y values, 10 minus 8, that's 2, and 5 minus 4 is 1. So it would be 2 over 1. Again, the slope would be 2. So no matter what points you pick for a linear function, you'll get the same slope, and as long as you're very consistent how you do the subtraction like we did it here. Now, if we plot these numbers, notice we have 2, 4 right here, 2, 4, and then we have 3, 6, 4, 8, and 5, 10. 3, 6, 4, 8, 5, 10. We plotted these and notice they form a nice straight line. So we figured out that the slope of the line is 2. We calculated it as 2, and we know that that's 2 over 1, rise over run, and we can see that it's up 2 over 1, up 2 over 1, up 2 over 1. So we know that the slope matches the slope of the graph up 2 units over 1, rise over run. But the point of this lesson isn't just to calculate the slope and look at the graph. The point of it is to think about it in terms of units, which is what we call rate of change. Attach units to what you're talking about so that you can understand what the slope is telling you. Because this axis here is the number of tickets I purchase. Notice if I purchase 10 tickets, it's going to be off the graph how much money I spend. If I purchase 2 tickets, it'll be $4 I spend. If I purchase 5 tickets, it'll be $10 I spend, and so on. So whenever I take a look at the units here, this is the ticket axis, the number of tickets I buy, and this is the cost, or the dollars axis. So when I calculate slope, I'm finding rise, and I'm dividing it by run. Rise over run, rise over run. But the rise is in units of cost, so it's dollars. And I'm dividing it by, because it's rise over run, which is the number of tickets. Dollars per number of, or dollars per ticket, I guess is the best way to say, dollars per ticket. That's the unit of what I'm talking about in terms of the rate of change. And the number that we got from this, the slope, was equal to 2, and the unit was dollars per ticket. So $2 per ticket, you interpret it the same way as miles per hour. If it were or kilometers per second, it would be 2 kilometers per every 1 second. Every second, another 2 kilometers. Every second, another 2 kilometers. Next second, another 2 kilometers. Next second, another 2 kilometers. Dollars per ticket, same way. First ticket, another $2. Next ticket, another $2. Next ticket, another $2, and so on. And that forms, since the slope is a constant, a nice line here. And we say that the rate of change of this thing is called the slope, and the rate of change in this case is $2 per ticket. I know it sounds like a simple concept, but when we get into higher math, rate of change is going to be very central to studying anything more complex than this. Because with lines, the slope never changes. It's always the same. But what if you have a curve? What do you do then? That's what we use calculus for, but the core of it is what we're doing here, rate of change. So I want you to think of slope from now on, not just as a number. A lot of times we say, find the slope, rise over run. That's great, that's awesome. Remember that. But I want you to think of slope as a rate of change. How fast is the y-axis changing compared to how fast the x-axis is changing? And that is going to unlock secrets and topics later on. So let me take this one down. We'll do another one, continue building your skills. All right, we're going to take a look at problem number 2. The table below represents a linear function, that means a line, shows the relationship between the years of service of an employee, how many years, and the employee's yearly paid vacation, which we call f of x. So if a person works 3 years at a company, they get 1 week off. If they work 9 years at a company, triple the time, they get triple the vacation. If they work 4 times the amount of time, 3 times 4 is 12, then they get 4 weeks off, and so on. So you can see this is linear because as I change the input by a fixed amount, the output also changes by proportional, but it's a fixed amount as well. That means rise over run is always going to be the same. It's going to form a line, and I'm telling you ahead of time, this is a line. So let's calculate the slope, and we can use any point that we want to find the slope. So usually I say y2 minus y1 over x2. minus x1. But I want to start to introduce the ideas of a function here. So instead of y, the output we really talk about being f of x. So what you might see it written as is f of x, comma 2, or subscript 2, minus f of x subscript 1. This just means the output, point number 2, the output, point number 1, which means the y values we subtract, and then x2 minus x1. Now this looks complicated, right? But I'm trying to break it down. I'm trying to show you that things look complicated at first, but they're not. All that's happening is this is the same thing as rise over run. In the past, we said subtract the y values, subtract the x values, but now we know that we don't call them y values anymore. We call them f of x values. Take the point number 2's f of x value, output, and subtract point number 1's f of x value, and we subtract them. This is just subtracting the outputs, which is how much the thing rises. And then we're dividing by the subtraction of the x values. Now, I do promise you, if you go into a calculus book and look at chapter 1, you will find something very similar to this in here because we're really starting to kind of encroach on more advanced topics. It's just that in calculus, we don't always talk about lines. Lines are the simplest case because the slope is always the same. But when you have a curve, then we have to talk about what to do, and that's what calculus is for. But you will see something that looks just like this because this is the foundation, and you can see how easy it is to understand what we're doing here. So let's go ahead and calculate this. We can use any 2 points we want. Let's use the bottom 2 here. Or let's make it easy on ourselves. Let's use the top 2 here. These are the outputs. So don't forget, like this point here is 3, 1, and this point is 9, 3, like this. So let's take the outputs. 3 minus 1. And the inputs, 9 minus 3. 3 minus 1 is 2. And 9 minus 3 is 6. So we get 2/6. Now we can simplify this. We can divide by 2 on the top and bottom. Divide by 2, we get a 1. Divide by 2, we get a 3. And the slope I get is 1/3. But don't forget, this is rise over run. That's true. But let's think about the units that we're talking about. Because when we subtract the top number, this unit really is, when we did this subtraction, it was the 3 minus 1. It was the number of weeks of vacation. It was weeks. And the bottom number was the years of service. So the rate is 1/3 week per year of service. That's the rate of change. This function is a line. It draws a line. When you work more years at a company, you get proportionally more vacation in a lockstep fashion. What is that number? It means that if you think about it in terms of rise over run, it means you get 1 more week of vacation per every 3 years, because that's what the units were. 1 more week of vacation per every 3 years of service you put in. Right? Look at the chart. 1 week, 3 years. And then for every another week you get here, you get 3 more years. So from here to here is another week. Let me think for a second here. For every, you're getting 1 week of vacation for every 3 years of service. Right, so 1 week for every 3 years of service. But then when you go here, you triple the amount of years of service and you triple the amount of weeks that you get as well. But another way to think about it, instead of rise over run, which is fine, you can think of it that way, is to think about the units. The unit that this works out to is weeks per year of service. What you get is 1/3 of a week per every year you work. Okay, so notice the chart starts at 3 years, but you only earn a week after 3 years. The rate here, a rate of change, is 1/3 of a week per year. So after the first year, you have 1/3 of a week of vacation. After the next year, you get another 1/3 of a week of vacation. After the 3rd year, you get another 1/3 of a vacation week. And since you've now worked 3 years, you have 1/3, 1/3, 1/3. You put them all together, you get that first full week after 3 years. But on a rate of change basis, it's 1/3 of a week for every year of service that you work. That's the rate of change. If we plot this, we can see the numbers 3, 1, 9, 3, 12, 4, 18, 6, 3, 1, 9, 3, 12, 4, and 18, 6. And you can see it forms a nice straight line. If you don't work any years at the company, you, of course, don't get any vacation. And then, of course, as you go for the number of years of service, it tells you how many vacation weeks you're going to get. And the slope of this line, we just calculated to be 1/3 rise over run. So that means 1 going up, and then 1, 2, 3 over, and then up 1 and over 1, 2, 3, up a 1, 1, 2, 3, up 1, 1, 2, 3, and so on. That's the correct slope. But the better interpretation of that slope as a rate of change means it's how fast this thing is rising, weeks of vacation, per how many years of service you have. So it's weeks per years of service. And the slope that we got was 1/3 weeks per year of service. So again, really, we're doing the same math as we've always been doing. We're just calculating slope, we're drawing a line, and I'm showing you that the slope is what we draw. But we're expanding a little bit. I want you to stop thinking about it always as just rise over run and think of it as the rate of change. It's how much the y-axis is going up divided by or compared with how much the x-axis is moving over. And attaching units to that really helps us understand the rate of change. How fast is this thing changing? Not too much. You only get 1/3 of a week for every year of service. The slope is not very high. That's what this means. Let me take this one down. We'll do another one, continue building your skills. All right, let's take a look at our next problem. The table below represents a linear function, that's a line, relationship between the amount of time a container of food has been in a freezer, time in the freezer, and the temperature of the container, which is f of x. So you can see the longer that the thing stays in the freezer, the colder it gets, eventually getting into the negative temperatures, okay? What is the slope of this thing? We can calculate the slope as, y2 minus y1 divided by x2 minus x1. Basically, we have to pick 2 points and we have to subtract and going the same direction. So we'll take 10 minus 6, or 6 minus 10. You can do it either way. But if you subtract this way, you have to subtract this way as well, 3 minus 1. And so what you get is 6 minus 10 is negative 4, and then here you get a positive 2, and so the answer you get is negative 2. So notice, first of all, that this is a negative slope. That just means that when we graph this thing, it's going to be slanting down because the temperature, of course, is going down. So let's graph it first before we talk much more about what this thing looks like. 1, 10, 1 hour means it's at 10 degrees Celsius. So there is a line right there. And then 3 hours is at 6 degrees Celsius. 1, 2, 3. And then we're up here at 6. And then 8, negative 4. Here's 8. And here is negative 4. And then 10, negative 8. 10, here's negative 6, negative 7, negative 8 right there. Like that. First of all, does this form a line? I think it does. Let's just double check. It's hard for me to tell with this angle if I'm doing it right. I do make mistakes all the time. Everybody makes mistakes. In fact, I think if you're not making mistakes, you're probably not doing enough problems, to be honest with you, because we all should make mistakes. So this is the line that represents the temperature of an item after you put it in the freezer, and it slopes down, negative slope. That just means that the temperature, which is the temperature over here, T, I guess I should put temperature in degrees Celsius is over here. And then little t, and this is in hours over here. So as time goes on, the temperature goes down. Eventually the temperature gets to negative, right? But what does this mean in terms of a rate of change? Negative 2. Well, what did we subtract? We subtracted 6 minus 10. That was the output, which was degrees. So the units were degrees per, or divided by, hours, because we subtracted hours on the bottom, hours. So the rate of change here is negative 2 degrees per hour. So you can think of negative 2 being rise over run. Of course, you can go down 2 over 1, down 2 over 1, down 2 over 1. That's rise over run, but we're rising down because we have a negative 2 there. You can think of it that way, but it's also important to think of it as a rate of change. What is the rate of change of the temperature? It is a negative 2 what? Degrees per hour. That means every hour that elapses, I go down 2 degrees. And so you can kind of pick a point here. If I go an hour in the future, let's say from here to here, then I go down 2 degrees, and that's what I went down here, 2 degrees for the next hour. The next hour here is 2 more degrees down. That's what it means, okay? So again, rate of change. Let me take this one down and we'll do our final problem. All right, here's our final question. The table below represents a linear function, that's a line, shows the relationship between the number of days before and after a theme park started a new safety system, x, and the number of repairs performed on rides, f of x. What this is basically telling you is that 5 days before any kind of safety system was implemented, and we had to do 10 repairs because we hadn't put the safety system in place. Two days before we did any kind of repairs, we had to do, or two days before we did the safety system, we had 7 repairs. But 3 days after the safety system was implemented, we only had 2 repairs, and 5 days after the safety system, we had 0 repairs. What it's basically saying is that once we put the safety system on this ride, then we didn't have very many repairs, because you can see 5 days after we implemented the safety system, we didn't have any repairs at all. And then going back before we did the safety system at all, of course, we had more repairs. So what is the slope, or the rate of change of this situation? So the slope is going to be the y values, the output values, divided by the input value. So we'll do 7 minus 10. You can subtract them any way you want. -2 minus a -5. Right? So what you get here is 7 minus 10 is -3, and this becomes a plus right here. And then 5 plus a -2 is going to be a +3, and so the slope is actually equal to -1. -1. But -1 what? What are we talking about? Repairs per days, I guess you would say. Repairs per day. Per day. It's a little bit hard to think about it, because what we're talking about is the number of days before a repair system was implemented. But let's just look at the graph and see if we can understand what we have here. -5, 10 is here. That means 5 days before we put the safety system in, we had 10 repairs needed. 2 days before the safety system, it was 7 needed. But after we put the safety system in, we had much fewer repairs, and 5 days after, we had actually 0 repairs. So the rate of change, you can think of it as -1, is going down, because of course if we put the safety system in place, then of course we require less repairs, and it's a straight line because it's a linear function like this. But the rate of change is what we want to talk about. Repairs per, I guess you'd say, day prior to putting the system in place. That's just another kind of unit or way of thinking about things. So here we've talked about rate of change. We've talked a lot about units, because in my opinion, rate of change and units, they go hand in hand. You can't understand rate of change of anything unless you're thinking about units of something to ground it in your everyday life. So I'd like you to think through these, and also try not to flush this information, because I know a lot of times you'll learn things and you forget them. I do all the time. But this kind of stuff actually is going to be useful for many topics down the road. So I'd like you to try to remember it. Follow me on to the next lesson. To part 2, we will continue to build your skills.